let me get started with the daily problem. And maybe I'll raise that question a little bit later. What is the daily problem? Again, it's going to have to do with dictionaries, which we've been talking about the last class. I want to review quickly. The dictionary operations are search. We are given a key, and we want to find out if a pointer to the item in the data structure, if an item with that key exists. Insert and delete are given pointers to the items. In the case of delete, an item that's already in the data structure. And then we wish to blow it away, okay, remove it from the dictionary. Min and max will tell us the largest and smallest item, and logical predecessor and successor will return the item before or after it. An item pointed to by X, okay? If we are, regardless of whether the dictionary itself is sorted, the operations will return these things in that kind of order. Any questions about that? Okay, so now let's go to the daily problem. And the daily problem asks us, they're saying we are given a balanced binary, dictionary data structure, meaning that it supports all of these operations in log n time, okay? So we know that somewhere there is a data structure implementation. Perhaps it's an AVL tree, perhaps it's a red-black tree, perhaps it's a 2-3 tree, okay? Whatever it is a data structure that makes these guarantees. And the questions now say, how do you use the, how do we use the dictionary to, this dictionary to do sorting in n log n time using the various abstract operations? So for the first problem, we're allowed to do min, successor, insert, and search. Those are the only items we're allowed to do. And we would like to use that to sort in n log n time. How do we do it? Does anybody have an idea? And again, I encourage people to speak. Any questions? Any ideas?
First, you find the minimum using search.
Okay, you say first find the minimum using search. Well, that I don't know quite what the first thing I got to do. The first thing I've got to do, presumably, is build my data structure. Does everybody agree? Because I've got the, I've got the, I've got a, when I say I've got an implementation, I've got code, but I actually have to pay a price to building the dictionary data structure. So what am I going to, let's see, what color should we use? Let's try this color. I claim the first thing I'm going to want to do is something that looks like 4I equals 1 to n, insert a sub I. Maybe I'm going to read these elements are going to start out in an array, or I'm going to read them. One way or another, I'd better start by building my tree. And the only way I can build it is by doing insertion operations. Okay? What is the next thing I got to do? You are now telling me something about min. What was that?
So you search for the minimum.
Okay, so now you're going to say x is equal to the min in my dictionary. Again, that's kind of, I guess, what we're doing. What's next?
You want to find the successor of that and keep inserting it. So
okay, probably what I think you're telling me now is you want to then print the successor, print what x points to, right?
yeah.
And you want a while loop around this and keep doing it. Oh, wait, no. Now you've got the min. You want to then move to the next one. And how are you going to do that?
Successor.
Successor. Say x is equal to the successor of x. And you want a loop that's going to go around something like 4i equals 1 to n times. Does everybody agree that this is an algorithm? I know it's not very clearly written, but actually, frankly, it's better than it usually is on a blackboard. Okay? Do people see what the algorithm is? First, we build the data structure through insertions, because there's no way you can do the insertion. There's no other way you get the data structure. And then we're going to find the minimum element. Oh, actually, except I think this minimum element should probably be outside the loop. Is that right? So probably what you want is something like my for loop here. Let me cross that out. And instead have my for loop go here. 4i equals 1 to n. Okay, and the loop is going around these things, the print and the successor. Okay, what is the running time of this algorithm? I think, does everybody sort of understand what I did? If not, I want to hear a complaint.
I have a question.
Yes.
What is the insert mean here? It's like we already have the data structure.
What if I already have the data structure? I have code, but until you have to pay a price to build your data structure. Does everybody, that should be clear. You don't have a data structure until you actually build it. You're reading in n numbers and trying to put them out in sorted order. So you have to pay the cost of building the tree. Does that
Okay.
make sense?
Yes, thank you.
Okay. So what is the running time of this algorithm? Let's try that. Maybe I'll try another color since it's bad. What is the running time? How much time does it take to build the tree?
N times.
I'm hearing n log n. Every insertion will take at most log n time. N of them are will take at most n log n time. It will take n log n time to build the data structure. Okay. Now, how much time will it take to print the elements out in sorted order? I have to find the min. How much time is that going to take?
Log n.
Log n. Again, I like hearing the screaming. Okay, log n. And then I've got a loop going around n times, which is going to print the item and find the successor. How much time does it take to print each item?
Constant.
Constant. How much time does it take to find the successor?
Log n.
Log n. What's the total amount of time spent printing and successoring?
N log n.
N log n. So what is this algorithm? It's n log n plus n log n. I claim that this algorithm is n log n running time. Any questions about that? Some people are complaining we didn't use search. Okay, so we didn't use search. Okay. See why that's n log n and see why we had to build the data structure? That's an important part of the cost. Let's try to do it another way of doing it. Here I'm going to allow myself minimum, insert, delete, and search. How do I go and use these operations to,
You would build the tree in the same way by inserting each node,
Okay,
and then
so you're going to say
afterwards.
start out 4i equals 1 to n. Insert, I'm going to say a sub I. Okay, what's my next step going to be?
Then you just keep finding the min and then deleting the min after that.
So
And you do
you
that
now
until
want
there's
to
no
say
nothing left.
4i equals 1 to n. You want to say x is equal to the minimum item, min in the data structure. You're saying you're going to want to print, I guess, x key, print the minimum item, right? And then what are you going to want to do? You're going to want to delete and then keep looping, right? So the next time you find the min, it's going to be what was the second in order, and so on. Does everybody agree with that? Any questions about that? What's the running time of this thing? How much time does it take to build the data structure? I get to play and change colors again. Well, how much time does it take to build the data structure?
N log n again.
N log n. How much time will this other algorithm thing? It's going to be n times what? How much time did it take to find the min?
N log n.
How much
Sorry,
time did it take to find the
Log n.
minimum?
Log n.
Log n.
Login.
How much time did it take to print it?
Constant.
Constant.
How much time did it take to delete the item?
Login.
So this total thing is n times log n plus 2 log n plus 1, which means n log n. N log n plus n log n is n log n. Does everybody agree this is another n log n item? Algorithm. Any questions about that?
Yeah.
This is how I
Professor,
want to think about data structures, by the way. Once I know what they can do, I want to use them to do things. And this is a great example. Question.
Yeah, I have a question regarding this. When they're asking us to sort the elements in a data structure, do we have to rearrange the elements, or do we just have to print them in a sorting order? Because here we are just printing them but not rearranging them in the data structure, right? We are not replacing or anything. We are just printing out in a sorting order.
Okay, here I am printing the items. If I had stored them in some array Q of, Q, I could have stored them one by one in Q and bopped up the counter for the ith element. I could have stored it as the ith element in a new array. Okay?
All right, thank you.
So, there's questions about, well, when you insert items into a binary search tree, they're ordered and then you can do things, and maybe. Okay, again, I didn't know that. No one said this was about. It's clear that building a data structure, a binary search tree, there's a lot of ordering in there. Okay, that's kind of what gives it its power. Arguably, if I just told you I had a dictionary and it did these things, it could have done it in some other way. But let's say that's basically right. Okay, any questions? Okay, good.
Is it not necessary to reinsert the elements after deleting them?
The answer is, do I want them reinserted? The only purpose I'm using this, in this case, the only thing I'm using my tree data structure for is to maintain the balance that I have, and I'm pulling them out. It's sort of like its insertion, it's sort of like its selection sort. And once I have printed out the item, I'm saying I don't need it anymore. If you need it, put it someplace. It would be wrong to put it back in this tree, because for this tree, I'm always wanting to make sure that I want to be able to find the next minimum. Okay? But I don't see any reason why I need to put it back anywhere. Unless if you have these items and you want them for some reason, keep them. Any questions?
May I add something? I don't think that would actually change the running time either, because it would just be another loop, like inserting those n elements, taking log n time for each one.
You mean storing them in a used tree?
So like if we deleted it and put the elements back in an array, we could just loop through that array once they're all deleted and insert them back again, and that would still be n log n time, I believe.
Okay, if I have an array that is done, if I have an array of these items and I want to rebuild the tree, I could always rebuild the tree in n log n. If I wanted to do something else with the tree after I printed out the items in sorted order, this is probably not the way to do it. I think the previous item, the previous search, what did I do here? Boom. In this case, I didn't delete anything, right? If I really wanted to keep my tree intact, note that this version of the algorithm kept the tree intact, okay? So if that's what you want, this is a better one. Any questions?
I have a
John will-
question, Professor.
Yes.
So given that since we're given a pointer to the element x,
Yeah.
why can't delete be O of 1?
Why can't delete be O of 1? Okay, so first of all, I didn't give you the magic of, well, let's think about this for a couple of reasons. First, remember back to how I did my deletion from a binary search tree. If you remember back to last class, I did give you a quick way to do it. And it involved finding, if I was deleting an internal node, suppose I delete the root, it involved finding the successor of the root.
All right.
It might be down at a leaf. That might take order, order log n time, or order height of the tree time, right?
Right.
So if that's a good enough answer for you, I'll accept that, okay? But it's an argument that if you, in a binary search tree, in fact, deletions can be expensive, log n expensive. It's not clear that it's a trivial thing. Okay?
Yeah, I get it now.
And especially if you think about a balanced binary search tree, there's got to be some magic being done to keep the tree from getting lopsided. If you took, I showed some discipline and didn't talk about exactly how you balance binary search trees. But there's this clever operation called a rotation, and you have to apply them in exactly the right place. Recognize that there's a cost for rebalancing after you did a deletion of an item. Okay?
So is the rebalancing included in the delete function?
Yes, yes.
Okay.
And with this problem, I guaranteed you I could do it in order log n time. And in fact, you can guarantee all of these operations will take no more than log n time. But in fact, they might take log n time on certain queries. Like when you deleted the root, having to find the successor all the way down the tree. Okay? Is it convincing why it is not necessarily constant? I think that should be convincing.
Yeah.
Okay, good. Then what's the last one of these? How can you use this dictionary to sort in order n log n time using only the operations of insert and in order traversal? Any ideas how we would do it?
I have an idea. You could just insert all of the nodes, insert all of the values, and then just do an in order traversal.
Boom, let me try to get back to 4. I equals 1 to n. Insert item a sub I. And now what are you going to do?
You would do an in order traversal?
In order traversal. Okay. What is the time that this will take? How much time will it take to build the tree? Okay,
And
somebody
login.
there has some private stuff going on in their life, but turn off your mic if you do. Okay, how much time does it take to build the tree? How much?
And log n.
N log n. Okay, and how much time does it take to do the in order traversal of the tree once you have it?
N.
N. This is n plus log n time. What does that mean?
That's n log n.
N log n. So all three of these are n log n. Which one of these is, in the worst case, which one of these is better?
I guess it would be the last one because n is well, wait, hold on. Yeah, n is less than n log n.
Okay, you're trying to say, well, maybe n plus log n is better than 2n log n.
I'm not that confident.
To this is, to me, they're all big O of n log n in the worst case. They're actually all theta of n log n in the worst case. And that tells me that these three are all run in the same time. If we implemented, would one of them run 3 times faster than the other? Probably. Would I know which one is the faster one? Probably not. Okay. The big O notation and the kind of worst case analysis we do doesn't really give me tools to tell which of the n log n algorithms is better, okay? All I know is that they're all equal in an asymptotic sense. Any questions?
If we have a specific purpose for the algorithm, could one be better than the other? For example, not deleting?
Okay, so some of you guys have fallen in love with the idea that you want to keep the tree together once you've built it. And that's not a bad idea. And if so, if you want it, then I think the first one or the third one looks the best, right?
Yes. Okay. Thank you.
Okay, if for some reason you're hostile to trees and you like seeing them cut down or cut down the size, you might like the second algorithm better. But on a big O sense, they're all three of them are n log n, they are the same. Any questions?
I had a question. So for this, like, wouldn't you like do some sort of like data analysis after you establish the big O, sort of like upper bound, to like see which one is actually like, you know?
So what I think you're saying is, suppose you really, really, really care about doing this efficiently. Okay? Skeena says all three of these are n log n. They're within a constant factor of each other, but maybe one of them is 5 times faster than the other. If you care about that, maybe it's not unreasonable to implement the three of them and pick the one that's best. Okay, if you really care about that. That is going to be outside my mattering zone in this class. Okay? But sometimes we are worried about the constants. As it happens, there's a problem that I'm working on with one of my graduate students. We had an idea on it last night. And in fact, there's a linear way of doing something that I can tell them that if they do it the right way, it will be 100 times faster than the other way, the way they attempted to do it. Does that factor of 100 matter? Maybe, okay. In our case, I think it will, because I think we're going to be dealing with a large thing. But in this algorithms class, does it matter? The answer is no. We're just going to be learning about the asymptotic analysis. And we realize that if you have a bunch of alternatives with the same asymptotic complexity, then you have to use some judgment which one you think is going to be faster, right? My money would probably be, if I had to say, probably this is going to be faster than the others. They're all going to build the tree in the same way. And this seems to have less stuff otherwise to do. But that's not the kind of reasoning I really encourage in here. In practice, if you have many alternatives, you should pick the best one. Any questions? Any questions about any of this? Okay, boom. Boom. Okay, what I'd like to talk about now is hash tables. And hash tables are a very, very practical data structure for maintaining dictionaries, okay? And the basic idea is that, as we have seen, if I have an array and I know that my item is in position I, looking up the ith element in an array is easy, okay? I just go to the start of the array times plus 8i times the number of bytes each element is, and suddenly I'm there. So looking something up in an array takes constant time if I know where it is. Hashing is a data structure that makes use of something called a hash function, which maps keys to indices, so we know where we will look it up. Any questions about that? So again, hash type function, I'm going to spend the rest of this lecture talking about hashing. And it's a little bit out of place in some sense, because almost everything else we're going to talk about in this semester is going to be about worst case analysis. As we will see, the worst case of a hash table can be bad. But the expected analysis of a hash table is extremely good. And hash tables turn out to be an extremely valuable practical data structure. It's something everybody should know how a hash table works, partially because it's usually a good thing to use. And there are other ideas associated with hashing that are kind of more important. And hopefully I'll get into some of those ideas a little bit later. But recognize that for today's lecture, we're going to be leaving the world of worst case analysis, okay? And entering the case of essentially something like randomized or average case analysis. Any questions? Okay, so how does a hash table work? We would like to have a hash function, h sub, let's say s, k, whatever, I'll call it k, that maps a key k to an integer between 0 and m. Okay, well, let's make it less than m. Okay. If this is true, we can interpret the value of the hash function as the index to an array. And this tells us if one way to represent my hash table would be to have an array of linked lists, okay, where I take my key, I hash it to get an index between 0 and m. Once I have that, I put the item on the, if I get the value of the hash function is I add the new element to the end of the ith, or to the beginning of the ith list. Okay? So when you're building a hash table, we're going to have this problem of collisions because we're going to be mapping keys to buckets, and it's not going to necessarily be unique. Two different keys might map to the same bucket. And so as our collision avoidance thing, the one that I think is the easiest way to understand how a hash table works is I'll have an array of linked lists. For each key, I'm going to call a hash function and determine which list it's going to be on, and then put it in there. That's what insertion's going to be. To search for an item, what am I going to do? I'm going to compute the hash function, the hash code of my item. That will tell me what list would it be on in my hash table, if it's in the hash table. Once I know what the list I'm on, let's say I'm looking for the item 8, I start looking, 8, h of 8 turns out to be 7. I search the list. Are you 8? No. Are you 8? Yes. Okay, I have found it. Okay. If I get to the end of this list and I haven't found it, that item is not in the hash table. Any questions with how this scheme, this data structure scheme works? Okay, I didn't explain it as clearly as I like to. So if there's questions, I don't mind hearing this. But do people see how I can use this hash table to store things? It's an array of linked lists. If I have n items, an array of size n, and I have about n items in my hash table, on average, each list is going to be of size 1. So searching through it should be fast. Okay, there's going to be some variance. Some lists are going to get unlucky and have more than elements than they should. And some will be so lucky they never get used. But the hope would be that the average bucket is going to be small. If the average bucket is of constant size, I should be able to search in constant time on average. I should be able to insert in constant time on average. Okay, any questions? Question.
You said on average and hope a couple of times there. So I'm guessing this, you could have one bucket that has all the elements and that wouldn't be good?
Right, so what's happening here? Suppose, let's say, first of all, suppose I have a terrible hash function that, let's say, what would be the worst possible hash function that for any key it returned the value of 0? Okay, this would be easy to write, right? You take your key, ignore the key, and return 0. Okay, what would happen? If that happened, every time I did an insert, it's going in here. And I'm going to have something like a linked list search. It's going to degenerate to searching a linked list of size n. So if I botch my hash function, it should be clear that this is going to be terrible because it's just going to reduce to linked list search. Even if I have a well-written hash function, I might get unlucky. And all the items happen to get hashed to 0. Now, if I'm not unlucky, but in fact, you have to be incredibly unlucky for that to happen with a well-written hash function. Okay? So that's why I have these weasel words. We're no longer living in where we're caring about the worst case today. We're going to care about what we kind of hoped is going to happen, the expected value. Okay? Any questions about that?
I'm not sure if I recall correctly, but isn't there a certain type of hash function that's like better than other types that causes the data to be like more well spread?
I will show you. Okay, we agree that mapping everything to 0 is the worst, God's worst hash function. Okay, I'll show you a much better one soon. The question of how these things are implemented, there are good, better. Let me show you what in a minute. I'll show you what let me show you, since you're interested. What is a good hash function? Okay. Well, what do we want from a hash function? What we want is that hash function will map our keys. Let's say our keys were names. Let's say you wanted them were strings. Maybe Skina is your string, S-K-I-E-N-A. We want to map that to an integer between 0 and m if we have a hash table of size m plus 1. We would like our hash function to have the following properties. It should be cheap to evaluate, meaning the time it takes should be linear in the size of my key. So if I have something that has n characters in it, it should take order n time to hash it. But if it's of constant size, like a typical name, that should be constant time. And it also uses all the values of the, of the space, the range from 0 to m, with equal frequency, roughly equal frequency. So the best generic hash function, if I want to come up with a simple idea for a hash function that I understand, one thing that I would do is first I would try to map my key, here a string, to be an integer. How can I turn a character string into a number? Well, suppose it's a text string. This is the way I would think about it. That if it's represented in something like ASCII, you guys know what ASCII is? Actually, I don't know if you guys know such things anymore.
Yes, I do.
You guys know the character set ASCII? You know every character from 0 to, every letter on the keyboard gets mapped to a number between 0 and 127, if I am correct. Typically, there's like that's a 7 bits. Okay, if you use an 8-bit ISO Latin, it gets mapped to a number between 0 and 255. Anyway, every letter of, every character is mapped to a distinct integer. What if I treat a text string, if it was a 7-bit ASCII thing, so the numbers range from 0 to 127, why don't I interpret a name as a base 128 number? Okay? Skina. What is the character code for an A? I don't know. Maybe it's something like a 40. Does everybody agree that, remember you looked that up, maybe 40 was the ASCII character for A, right? What was the character for E? I think that would probably be something like 45 or 44 if I am adding up right. Maybe this is 49, 44, well, that's 49. Maybe this would be 53, 54, and 62. Don't quote me on that. But does everybody agree that each character gets mapped to an integer? I could think of this array of character values as being a base 128 integer, right? You guys are used to base 10, right? How would I interpret this as a base 128 integer? Well, I would multiply 40 times 128 to the 0. I would multiply 54 times, what is it? 128 to the 1, right? The next one I would multiply by 128 cubed to the 4th, to the 5th, to the 6th. Does everybody see what I'm doing to interpret this as a base 128 integer? What is the number 1561 as a base 10 integer? That's 1 times 10 to the 0 plus 6 times 10 to the 1 plus 5 times 10 to the 2. Remember that? All I'm doing now is converting this thing to a base 128 integer, or interpreting it as a base 128 integer. And when I compute this thing, I'm going to get a number. It is a big number. Does everybody see that it's a unique number for every string? Okay. Now, a hash code requires, so the first step was to map it to a big integer. And this is going to be a big number. Does everybody agree? Once I have a big number, what am I going to do? I'm going to take that number, mod the size of my hash table. If I take this big number and I take that mod the size of my hash table, that's going to give me mod m. That's going to give me a remainder. The mod function, remember, computes the remainder. The remainder mod m is going to be between 0 and m minus 1. Does everybody agree? So now I've got a number that's in the range that I want. I've taken every key and mapped it to a number within the range that I want. Okay? And that's what I'd like to have my hash table do. Any questions? The reason why this works is the same reason why a roulette wheel works. Does anybody know what a roulette wheel is? You ever go into a casino, you see this thing? What happens when you go into a casino? There's this roulette wheel, and I'm going to try to draw such a thing, and it's got the numbers, 0 through 36, if I am correct, written on the wheel. And there are these 36 slots on the wheel where the ball can end up. The dealer then says, place your bets, last call, and they spin the wheel and they set the ball rolling on the outside of the reel. And it goes around and around and around on the outside of the wheel. And when it starts to slow down, they say, no more bets. And the ball eventually drops down. Uh-oh, now I'm in big trouble. And it goes ka-chunk, 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 and lands in one of these spots. One way to think of what a roulette wheel is doing is it takes the long path of the ball on the outside of the wheel, and it's taking the remainder, dividing by 36, remainder mod 36, to govern which slot it's going to be in. Does everybody kind of get that idea? There's the long ball path, There's 36 different possibilities. The path that you end up with is the remainder, okay, of the number of trips after the number of trips around the wheel. What's the last part of the trip that mattered? Okay? And this is uniform. It better be uniform, or else no one's going to want to bet in the casino, right? And it better be random, or use these things equally, or else, again, somebody's not going to be happy with this as a gambling operation. Does everybody kind of see the analogy between this, convert to a big number and cut it down by mod to the idea of the roulette wheel?
I see it. That's a good analogy.
Okay, good analogy. If you went into a casino and the dealer put the ball down and didn't spin it and just let the ball go bloop, and it fell right into the spot where they did that, would you consider that to be a fair thing or was the dealer trying to make the outcome happen? Obviously, that's one way you get the bettors to rebel, okay? But if they have a long path, it's clear that the dealer doesn't control the outcome, and that's what's going on here. Any questions now about how this hash function works? I can interpret any stream of bits as a base, whatever the byte size of my data is, number. I can convert it to a number. I can take the mod, and that gives me something within the range that I want it to be. Any questions about how the hash function works?
Going back to the algorithm where we converted the string to a number of base 128,
yeah.
If we entered a string that was like an anagram of Skeena, would it technically land in the same
Okay, so
like,
now this is
bucket?
an interesting question. Suppose we rearrange Skeena's name. We said anagram. Let's say that it was, KSEINA. Would that yield the same hash code? If I was just adding up the characters, it would. But notice that I'm not adding up the characters. I'm weighing them by their position. Is the number 561 in base 10 the same thing as the number 165? No. And the reason is because there is this weight by position, this positional weighting scheme. So that's one of the things I did to build resiliency into this. There were other ways I could have converted it to a integer. But this is one way to, that is more likely to generate a relatively unique integer. Okay? Any questions? Any other questions about the hash codes, where they come from? Okay? This turns out to be a very powerful idea to take a, a key, a data item, and map it down to a smaller integer to be its representative. Any questions about that? Okay. I say, what is the key length? You could do this, you could hash strings that are as long as you want. Okay. The number that you get is going to be a function of whatever your modulus is. The final code is always going to be less than m if you take that big number mod m. So I can take as big an item as I want and hash it down to a distinct integer from 0 to m. Any questions? Okay. Tell you what, let me move on a little bit. Now, again, it's funny, if I had you guys live, okay, there's a difference between good and bad hash functions in practice that I'd like to illustrate with by looking at people's social security numbers. Okay, so if I had you guys live, I would do this. But for those of you with cameras or the ability to type yes, how many of you have a first digit of your social security number that is 0 or 1? Type yes. Boom, boom, boom. These people going crazy here, right? Nothing but zeros and ones. Now, so how many of you, okay, let's stop. That's enough. How many of you have social security numbers ending in 0 and 1? 0 or 1. Now type it. If your social security number ends in 0 or 1. See little bits of typing, but I don't see that as, it's typing much slower, right? More of you have social security numbers that start with 0 or 1, then end in 0 or 1. Okay, why is that? Does anybody know?
Does it have
Turns
to
out-
do with birth?
Yeah, what?
Does it have to do with birth year?
Has to do with birth year and
location?
birthplace. Okay, many or where you get your social security card. You guys, I can tell from looking at you, are New Yorkers. I don't know by looking at you, by knowing what school you're registered at. That's why I can tell, right? And New Yorkers happen to be assigned a chunk of social security numbers at the beginning of, between with either zeros or ones. Okay? They then do it among all New Yorkers, they then apply it sequentially. So the last digit is, basically 1 out of every 10 New Yorkers has the same last digit. Okay? The last digit is would be good for a hash function because that's going to be unique. The first digit would not, because that's there's some kind of systematic reason why that's being given. A good hash function is one that is going to have the property that it is going to serve to be essentially random, meaning it uses these things uniformly. Any questions? Okay, now one of the interesting things about when you analyze hash functions is what is the likelihood that after you've done, in an ideal world, if I insert multiple keys, if each of their hash codes is randomly determined, I want in my hash table there to be no collisions, because then my linked lists are as short as they can possibly be and everyone is happy. If I have a hash table of n items, let's say I have room for m items, how many insertions, after how many insertions do I know there has to be a collision? Okay, I've seen m plus 1, right? I can, if worse comes up, I get very lucky, every bucket's gonna have 1, and then the next one will cause a collision. What's the fewest number of insertions till I get a collision if I am unlucky?
2.
2, right? If I got unlucky, the first 2 items go in the same bucket. Okay? In fact, how long should it be till I expect that in some bucket there's going to be a collision? And it turns out to be surprisingly frequent. This is something they call the birthday paradox. What's the probability if I have a hash table with m spots in it? What's the probability that there's no collision after I've done n insertions? Well, after I did the first insertion, well, there's going to be no chance that I had a collision, right? There was nothing to collide with, m over m. After I inserted it, if I have m buckets, what is the probability that my next insertion is not going to have a collision? Well, I've got m minus 1 places it can go, m minus 1 over n. The next one is m over 2 over n, dot, dot, dot. In general, the probability of having no collisions is the product of m minus I over m as I goes from 0 to n. If we plot this thing, something very funny happens. Actually, let's see if I can make this go away. That's a problem. That would be better. Boom. It turns out that by the time you have, this is showing me what's the probability of no collisions as a function of n. By the time you get to about 22 people in a hash table of size 365, you are likely to get a collision. Right now, I have in my class 118 people seem to be on here. There are 365 days in the year. Are there two people in here that have the same birthday? Of the 128, almost certainly. It might be that you could get 365 people in a room with no collisions, but that's extremely unlikely. Actually, on my Zoom page, I am seeing 25 people. Odds are, just among the 25 people on my first page, 2 of you share the same birthday. And the reason why that is true is the reason why we need to be able to worry about collisions in in hash tables, and why we need things like linked lists, techniques to resolve the collisions. Any questions about that? Okay. Boom. Okay. What we should now believe is that the following is at least kind of true. Okay? That if I want a data structure, again, this technique of using linked lists to maintain the hash table is called chaining. There's another way of collision resolving where if I put my spot in an array and it's already filled, I put it someplace else. Okay? Either way, we would expect that search should take constant time. Why? I hash my code, I go to the bucket, my linked list should be, if I'm not unlucky, of constant size. It'll take constant time to search. If I am unlucky, it will be order n. In an insert, okay, actually every time I insert it, if I insert it at the beginning of the list, actually, every time I do an insertion, it should be order 1. Okay? But to delete something from a hash table, I have to actually find what bucket's in. I then have to search the list. I claim that that should still be an order n operation. So in expected time, the main dictionary operations take constant time. That's why hash tables are good. Some of these fancier operations we defined, like finding the min and the max, the predecessor and successor, the hash table does absolutely no good for it. Where in a hash table is the minimum element? Does anybody know where the minimum element is? It's somewhere, okay? If you want to know where, you got to search through all the elements. Or you've got to do one of these things with, maintaining it in a separate place and keeping track of it. Any questions? So pragmatically, hash tables are often the right thing to use for dictionaries. There is a reason why you guys are used to using hash maps in your Java or whatever other language you're using, because these are practically very good data structures.
I have a quick question, sorry. Couldn't we do delete in constant time with doubly linked list?
Okay, so if, as I told you, if you have a pointer to the item, and again, you're right that if I'm maintaining, if I'm keeping my word about what a dictionary should do, then you're right. Keeping a pointer, if I have a pointer to the item and I've maintained it as a doubly linked list, you're right, then I should be able to delete it in constant time. If you want, I will say that is constant, okay? The big problem with a hash table is that potentially, if you are unlucky, the time it will take to do your deletion, okay, hold on, bang. Your search is going to be order n. This is where the problem potentially comes in. But you have to be very unlucky for that to happen in a good hash table. Okay, does everybody kind of get that idea? Okay, anyway. But if you're worried about worst case analysis, the best thing for worst case analysis are balanced binary search trees. And since most of the time in this class, unless I tell you, you're doing a randomized analysis or an average case analysis, you'd better assume you're doing a worst case analysis. So if I ask you for something and you're using a hash table, I will mark that wrong because that's not going to guarantee you a good worst case time. Any questions?
Could you please clarify why you changed the worst case to constant time for delete again?
Why did I change this to a, okay, so let's think that I am, actually, it's interesting. Let me tell you what, if we're thinking about the hash table implementation, like I said, which is that we have an array of linked lists and we have a linked list and we kept it as a doubly linked list. If we're assuming the delete operation is, as I said, you're given a pointer to the item to delete, then in fact, to delete that item, you should be able to do that in what you call it. Basically, it's just a question of removing the item from the linked list. That's why it would be constant time. Okay? Any questions?
I'm sorry, I just missed when you said something about marking something wrong on an exam. Could you repeat?
This part was interesting, right? You want to know what will I mark wrong? If I tell you, give me an n log n algorithm for solving this problem, and you say, well, I'm going to do n things that are involved looking up something in a hash table. The worst case time to look it up in a hash table is order n. N times worst case n is n squared. That's not order n log n. In expected time, it might be, okay? But that's not, when I ask for, assume I mean worst case in general. Hash tables don't give you a good worst case bound. So you shouldn't be using it for a problem unless I'm explicitly telling you you're doing something randomized or average. Any questions?
Wait, so couldn't the same be said for a binary search tree unless you say that it's balanced? The worst case for like.
Well, I'm going to let you assume that you can say to me, I'm going to use a balanced binary search tree data structure. Okay. Now you can go to an algorithms book and see how it's implemented, and it's implemented. By using that, every operation will be log n. That's how your sorting algorithm worked, right? Your sorting algorithms I just talked about on the daily problems all took n log n time because you were using a tree that gave you a guarantee, like an AVL tree or a red-black tree or a 2-3 tree, okay? If you said, oh, I'm going to use a hash table, you lose because in the worst case, it's not going to be log n per operation. It's not going to be constant, it might be order n. Any questions? So for today, we're allowed to use hash tables. Beyond today, make sure that you're generally, I want you to use worst case analysis. Now, the reason I'm going to let you think about what you call hash tables today are that they are in practice, very, very important things. Okay? I once heard a good algorithms guy who became a vice president of engineering at Google. Okay? And he once gave a talk about what were the algorithms they use at Google. He said hashing, hashing, and hashing. Okay? And I'd like to give you some idea as to why hashing is such an important thing. It's not just a question of building a hash table, okay, and using it like any other dictionary, okay? Hashing lets you do some things that are different than just normal dictionary operations, okay? Suppose you are Google. Google has this thing that crawls the web and gets looks for new articles every day, right? New web pages. Now, suppose, let's say, it sees a document. How does it know it hasn't seen it before? Unfortunately, many people have pirate copies of my book, okay? How do you know that when you're crawling something, does Google want to store many copies of my book? No, they want to store at most one. So they'd like to be able to know of all the documents that Google has in its index. When they crawl a new document, is this thing in the index already? Okay. How can you do that? One possibility is you take the new document you crawled and compare it one by one against every other document you have already checked if you're Google. Well, Google has billions of documents on the web. Is Google going to spend order of billion time checking the new document against every of the other ones to see that it's unique? How can it do that more efficiently? What if it builds a hash table? Let's think of it as a giant array, in this case, of bits. Let's just think of it as a Boolean array. Okay? And it has one bit for every possible hash code. Maybe it sets m to be equal to, 2 to the, 30 or something like that. Some big number. 2 raised to the 30. Maybe 2 to the 32, who knows? Okay? Now what they're going to do is to set the ith bit to be 1 if there is a document that is already seen with that hash code. Does everybody agree that if I have an array of size 2 to the 32, there are 2 to the 32 different indices? If I use this as a bit vector, where I store 1 bit per item, if the ith bit means that there is something that I have seen on the internet that is of size, that has a hash code of I, okay, I set it to be 1. What's going to happen with Google? They take a new document. They compute its hash code. That will tell them that the hash code of that is J. If the bit in the jth position is 0, it means there has never been a document Google has seen before with this hash code. It must be a unique document. If it sees a 1, it means that there is a document with that hash code already. So what should Google do? Perhaps it should look and compare those two documents. Or perhaps Google will say, I don't care enough. Okay? If this hash table is big enough, it's going to be very, very rare to have 2 items hashed to the same, 2 different items hashed to the same bit. And so maybe I'll just even make the assumption that if that bit is used, this document is already there. Does everybody kind of get that idea? I'm not even keeping a linked list anymore. I'm just keeping a bit vector. But because I have this hash code and it's got a huge space, if there are only 2 to the 20th, 2 to the 20 documents, that's a million. That's not, okay. Then it would be very, very rare that any 2 codes of size 32 bits would collide. If I had a hash code of size 256 bits, if I built a hash table on that, okay, I claim it's going to be almost certain the only time you're going to get collisions between documents if they're really the same thing. And you can throw out the new document without even looking at it. Any questions about that? Do people see how I use the hash table to identify duplicates very, very quickly? In constant time, for the new document, all I have to do is compute its hash code. That's the length of the document. I'm then going to check 1 bit instead of doing something that is big O of the size of the web. Okay? That's an amazing difference. Any questions about that? Okay? See how I could use hashing to do this quickly? Okay. Any questions? Okay. Now, what if I wanted to tell whether a document, let's say that I was a, let's say that I didn't trust students, okay, or the academic establishment did not trust students to always turn in their own work. Have any of you ever had your assignments run through a plagiarism detector? Okay, some system to make sure that you haven't stolen your term paper from someplace? Is there anybody, your teachers check for this? I see one person saying probably. Okay, trust me, all you guys have been checked out. Okay? How do you implement this thing? Well, if you were worried about exact matches, did you turn in exactly the same assignment as somebody else? Does everybody see that the Google solution is exactly that? If I have a hash table where I hash every document I've ever seen and keep a bit for this, for every document that I've ever seen, if I take your term paper, I hash it and I go to a bucket with a 1, that means that there's somebody else has already turned in a document with that hash code. You are probably guilty. If it got hashed to a bucket with a 0 in it, you are presumably clean. Does everybody see how this would prevent exact matching of documents? Okay. Now, suppose you were a dishonest student and you knew your teacher was doing this. What would you do to prevent your term paper from being, the term paper you have carefully stolen, from getting caught? What would you do? Anyone? Don't hand it in. That's a good thing. Okay? But suppose, let's say you want to test the system. If you change one word or one character, does everybody agree that should change the entire hash code? Okay? So this would not be resilient to you changing little bits of the document, right? Okay? So does this mean that that's now the secret? Okay? Well, the truth is people build more sophisticated ideas based on hashing. How would I go? Have any of you guys had to run any of your computer programs through this programming system called MOS? Does anybody, for any of your programming assignments, I see one person, some people recognize it. Yeah, in many of your classes, all your assignments are run through a plagiarism system. If you could get away changing one character in the program, there'd be a lot more bad CS majors than we have now, right? How can we catch those? Well, what if I take your document, your program you submit, and I break it up into windows? Let's say that if you have a document, and I ask, let's say, every consecutive sequence of 100 characters. If you have a string of length 100 that's still in common with something in the hash code, if I hash substrings of the text, does everybody agree that I will now get suspicious? I will get a collision if there is a substring of the document that matches a substring of something I have already seen. Does everybody see how I can do that? Okay, any questions about that? I hashed the first 100 characters. I hashed character 1 through 101, 2 through 102. And in all cases ask, is there a string of 100 in one of the other files that got matched to that? Does everybody see that? Okay. Now by comparing windows, if there's anything in common, a big enough piece in common, I can nail you. Okay. Any other questions about this or how these plagiarism detectors work? Okay. Would it still have to be manually reviewed since collisions can occur? Well, that depends upon how mean the teacher is, right? Okay, we'd like to think, a sufficiently mean and bad teacher would immediately throw you out just because your window collided. A smarter thing would the right way to use these systems would be that you use that to suggest pairs of documents that require looking at. And now I would get a report that says, yes, this document seems to have a window in common with that document. I look at the two documents and now I can make my judgment. Okay? Any questions? Okay? Getting another question that's actually kind of interesting. You're saying that if you hash every one of these strings, won't it, now the size of my hash table is not going to be order the number of documents. It's going to be order the number of windows, which means I'm going to have an entry for essentially every character in my every position in every document. And now you're saying, doesn't that make the hash table big? And the answer is it could. But there actually are other hashing tricks that can make it likely that I keep only the strings that are most interesting, most representative. Okay? And, and there's something called min-wise hashing, if you're really interested in that. There's some very interesting techniques, which I don't think I'm going to have time to talk about today. One thing called min-wise hashing is a way to hash windows and yet make it likely that I'm going to catch a bad guy, even using less memory than keeping all of them. Okay? Any questions about that? Any other questions about how you use hashing for, things like plagiarism detection?
If you decide to have like a position for each position in the document in the linked list, wouldn't that just be a constant times each document?
Okay, so you're saying that if I have a window, should I care? You're really questioning whether I should care about the fact that if I have, instead of hashing each document once, I hash it for every text window in the document. Notice that if I have a document of length n, instead of producing one hash code, I'm now producing something like n hash codes. So if I have short documents, I shouldn't care. But if I have long documents, I would care. If you take Skinner's book, how many windows of 100 characters are there in Skinner's book? Well, there are, several 100,000 of them. Okay? So it's not unreasonable for people to be worried that the hash table would get too big. Okay? Any questions? But like I say, there's other clever tricks to minimize the size of the hash table if that's really what you're worried about.
Yeah, I was just operating under the assumption that every document is relatively the same size, but I guess if you're comparing your manual to an article, then there would be
okay, if you have long documents, it would be expense. Okay. Again, the upper bound is the number of documents by the length of the documents. Okay, and that's could be much bigger than just the number of documents. Any questions? And there's other clever uses of hashing. One that is kind of interesting is, how do I convince you haven't changed your file? Okay, so suppose, let's say that you're telling me I am going to, let's say there's going to be an auction, and you want to bid on an item. Suppose we're selling something. Suppose we're selling a house, and I'm going to sell it to the highest bidder. Okay? In a closed auction, everybody sends in a bid, and then I open up all the bids and give it to the winner. Right? Now, you might not want to mail me your bid. Why? Suppose you're afraid somebody else is going to read your bid and bid $1 more. How can I collect your bids without actually knowing what your bid is in advance? Well, suppose you wrote your bid on a file. I'm going to buy Skeena's house and I'm going to overpay $1 million for it. Okay? Now, somebody else who wants it could very well, if they knew that, they would do what? They would have a bid of $1,001,001, right? How can I make sure that people can send me bids without letting them, without actually getting the bid and not letting them change it? What if I have them instead give them a hash function and tell them, compute the hash value, H of this thing, which is going to come out to be 639. And the hash thing of this, which may come out to be 1,256, right? Now, after the deadline is ended, I ask you to mail me your bids. Now, you're going to send me a document. This guy is going to send me this document. I can compute the hash code of this document and make sure it is the same hash code that the guy had sent originally. Does everybody see that they can't change the thing and have the hash code be the same thing? Suppose this person, okay, suddenly learns that 1,000,000 was the winning answer, okay? If they try to change the document, the hash code is going to change, and it won't match the hash code that they sent earlier. Does everybody kind of see this? If I compute the hash code of a document, if somebody later changes the document, the hash code is going to be different. And this is a way I can protect against changes. There's something called cryptographic hashing. Any questions about that? Okay. Is it possible to give a hash code of the file that's slightly changed? Okay. Well, this is now, if I have a good hash function, very hard. You're saying, can I change the file to mean what I want it to mean, and yet have it have the desired hash code? Now this is a problem, right? Changing it arbitrarily will produce a different hash number. It's very hard to change a file, so it means now what I want it to mean while hitting a good hash, a desired hash code. Okay, if I have a good hash function. Okay, and this is the idea of cryptographic hashing. Any questions about that? Okay, so I'm going to leave this be here, and let me give one last example. Okay, again, of just hashing as how you might use it. It's often the case that you can kind of, the idea of hashing is you can take a big thing and map it to a small thing that means something. Okay? Suppose I want to know whether two words are anagrams. Let's say I give you a bunch of words. Okay? Let's say I give you a set of n words. And I want to know whether any two words are anagrams, meaning they're rearrangements of each other. How can I, how can I do that? Well, one thing I could do is I could compare every string against everything else, but that's expensive. What I could do is to take the every string and rearrange the letters into a canonical order. Let's say by sorting them. Now, two words that are anagrams will have the same code, right? If I sort the characters in the word dog, I get DGO. If I sort the words in God, I get DGO. Does everybody see now a collision of these codes means they have the same characters? This is a hashing-like idea, okay? And looking for duplicates is a way of telling whether or not I've got a collision. Any questions about that? Okay, bottom line, for today, hashing is a great thing to use. It's a very practical data structure. It's good for a lot of things. You should be aware that this is a tool in real world, just not in analyzing worst case complexities of algorithms. Any questions? If not, thanks for your attention, and I will see you guys next class.